All right, at 7:30 Pacific time, September 24th. My name is Timur. We have Seth with me on the line. We are restarting our webinar series at Mat3ra.com. And today we're going to be focusing on the two-dimensional materials and the design capability that we've been working on over the last few months. There's quite a bit of new capability that is focused specifically on designing monolayers, interfaces, surfaces, and related features. For example, if you go to the next slide, so we can see some of the structures that you can design with the open source, open access code base that we've been building at Mat3ra. And all this capability we've named Mat3ra 2D. And today Seth is going to tell you about some of the basics of our approach, the layout of the code base, what's possible, how you can design things like moly-sulfide, graphene, surfaces, including defects, including some realistic features that we have to deal with when we need to study two-dimensional materials. So these are some of the possibilities. We will be speaking about this over the next few months, progressively making it more and more complex. We start with the basics today and then continue with defects, passivation, perturbations, and the rest. Now, let's go over the rules of engagement briefly. If you go to the next slide, the goal of this webinar is to present you the capability that we have at Mat3ra.com. We expect every participant to be a registered user so that you can follow the content. However, the code base is open so that you can download and run the code base on your own without having to be a Mat3ra user. We'll share this presentation both through email and on our YouTube channel, so there is no need to take notes. Now, if you want to ask questions at any time during this presentation, you're welcome to do so. There is a Q&A portion, and then there is a chat portion of the Zoom application. You can use both to ask questions at any time. We'll have a dedicated time to answer them. All right. With that, and without further ado, Seth, the floor is yours. Please go ahead.
Thank you, Timur. Greetings, everybody, and welcome to Mat3ra 2D webinar series. My name is Seth, and I'm going to present you a Python package for the design of 2D materials. First, let's look over a presentation, which will give you an overview of our approach, and then we'll get to hands-on experience. One of the challenges in material science today is that most of the data used to train machine learning models is data of ideal 3D crystals, while real-world applications require structures that are more complex, such as surfaces, interfaces, and defects. So we need a way to generate such materials. For that, we created easy-to-use framework for materials design. Our approach has well-defined data structures to help organize information in database and make it easier to build machine learning models. We demonstrate the application of our approach with a set of Jupyter notebooks that can be ran in any web browser. We primarily focus on 2D materials because we believe this is the area of increased interest. It is important for electronics and semiconductor research. Also, most of the interesting processes occur at the interfaces between materials, and the field is rapidly growing. Here are some examples of the structures that were generated using our package. So we have grain boundaries, passivated grain boundaries, interfaces with intercalation, sandwiches, and other forms of interfaces. Our implementation has 5 components. First is the data standards housed in Mat3ra ASI package. It has JSON schemas for all of the data structures for materials, transformations, and other physical properties. Next, we have commonly used examples, which is housed in Mat3ra standard package, and it has examples of entities that adhere to the data standards. Third step is the abstract code housed in Mat3ra code package. It has all the necessary implementations for Python and JavaScript runtime to make the make the package available. We're not going to go into details today. It's used internally, but it's open source, so you can check it. Then the next one is a specific code, which is Mat3ra made package. And it's the main code base that has all the functionality to analyze, construct new materials, and operate with them. And the last one is the code usage examples stored in Mat3ra API examples. And it consists of a set of Jupyter notebooks that showcase how to use our approach. So first is, as I mentioned, is a JSON schemas standards in Mat3ra ASC package, and it defines schemas for materials, common physical concepts, and operations. Next, we have the standard data package that has most commonly used structures. For example, today we're going to be using some of the materials that are stored there. And as you can see, names for the materials have categories and other properties in them to make it easier to search for them. The main package is the functional source code, implementing class instances and methods to work with the materials. So it has definitions for main concepts such as material, lattice, basis, and cell. And it has a set of tools that has all the builders, analyzers, and other classes that help you implement, that help you create materials. And the final component is a set of Jupyter notebooks demonstrating the usage of the package. They are constructed in a self-documented manner, so the user can read description and follow through each step to understand how to use package and how to use this, this particular notebook. They can be used as a tool to generate materials in your workflow. You can use them as a templates, add your own specific functionality, and it is easy to share across the team and easy to reproduce for team collaboration. The last stage is making sure that functionality is available to the user. We support running all the notebooks in familiar applications such as JupyterLite, but also we make it available on a JupyterLite environment, which runs with PyDiet kernel, which is a Python running completely in a web browser. So you don't need to install anything. You can just go to the link, open notebooks and run them. You can drop additional files and notebooks here as well and use them. It is accessed via Materials Designer. And also you can use any pure Python package, such as PyMagen and ASC, as well as our Mat3ra made package to create materials. Let's look over the implementation details. We split process of material creation into parts: configuration, transformation, and the result. For example, if you want to create a slab, we start with a bulk material and provide physical properties for the target material, such as meter indices, thickness, vacuum, etc. Then we use the slab builder with a set of its own parameters that define how material is constructed or presented. For example, XY supercell, whether the surfaces are orthogonal to the axis, and others. Then builder applied to the configuration yields the resulting material, which stores all the transformation data in the metadata for provenance. Sometimes you might not know all of the properties, all of the parameters for the configuration right away. For example, for the interface, you need to match two parts. And it's done by providing supercell matrix as well as strain matrix for the film. So in that case, we need to make approach staged, where we have define, refine, and build stages. So for the interface, we need to define the slab configurations for film and substrate. And then to get to the interface configuration, where you need to provide matrices for the supercell. We use ZSL interface analyzer with its parameters such as maximum area, and it yields a set of interface configurations which are ranked by strain and size of the supercell. And you can choose what's best for your use case. Sometimes you need lower strain, sometimes you need lower size of the overall structure. And then you select the interface configuration that you need, and you apply interface builder to it, and get a result with the interface with the all metadata stored. To make it easier to find specific materials and reason about them, we proposed a categorization for materials that we use in standards package as well as made package. At the top level, we have materials divided by domains of pristine structures, compound pristine structures, defective and process structures. Then they split by dimensionality, ranging from 3D to 0D. And further down, each of them has its own category. For example, ideal crystal, slab, interface, or point defects. And we also have variants which show, which split each material even further to show how it was acquired. So, for example, for the interface, we have simple, ZSL interface, twisted interface, and others. Today, we're going to focus on a subset of them. So for 3D, it's going to be ideal crystal. We'll show how to import and visualize it, a slab, and the interface will cover simple and ZSL interface options. So for hands-on demonstration, we will go over Materials Designer app. It's how is it accessed, its main UI components, and then we're going to look into the Standata materials repository, how it's used inside the Materials Designer, how you can search and import materials. We're also going to import materials from the file system. Next, we're going to look into the JupyterLite environment. We have a dedicated link for the notebooks themselves, as well as the JupyterLite transformation, which is included inside the Materials Designer. We're going to use primarily this one today. And we're going to use all of this functionality to create some slabs and interfaces with the use of helper functions and notebooks. So this is the UI of Materials Designer. We're going to look into it later. First example is going to be a simple slab. It's going to be silicon 001 slab. It's pretty straightforward. We want to take the silicon bulk and transform it into a slab with some thickness and added vacuum. First, we start by importing material. We do this with the help of Standata. It can be viewed as a static database that you can query. For example, with the help of this function, we can search by the name. We can search for any part of the name that I've shown previously. Each material has in the Standata. This configuration returns a JSON file that has the structural information about material. To make it available for analysis and transformations, we need to convert it into a material instance from made material. Just create instance from this configuration. Next step, we import the create slab helper function. We pass it the substrate, bulk substrate that we've defined before, and then we specify familiar properties such as Miller indices. In this case, termination formula, if you know one. You can pass none or omit the field altogether to get the default termination. For example, for silicon, we have just one termination. Then we specify number of layers, which is provided in the number of unit cells. you specify vacuum, and then the properties for the builder parameter. So XY supercell, what's the supercell matrix of the final material, and whether we use the surface orthogonal to C. So in this case, it's true. And that we use conventional cell for defining the Miller indices. Also, if you use conventional cell, this means the thickness of the final slab is calculated using the conventional cell C lattice vector. If you specify false, then the primitive one is used. And then when we run this function, we get the slab. So we see it's 3 conventional cells thickness, it has vacuum of 10 angstroms, and yeah, just one unary supercell. Let's now look into hands-on experience. This is Materials Designer. We followed the link, and we have the silicon material as a default one. We go to Advanced JupyterLite Transformation, and then we're presented with the window for JupyterLite Transformation. At the top, we see materials in input, where we can select materials. So any first material from the working directory is automatically pre-selected. So we can select silicon FCC. Here in the body, we presented with the introduction notebook, which has all the content of all the notebooks, and they are structured according to categorization. And on the left, you can see all of the notebooks in a flat list. So to find the slabs, we go to single materials, to the structures, slabs, create slab from bulk material. Press it. Then we presented with the notebook for slab creation. And as you can see, it has the usage description. So it explains how to use it. Usually, the most important part is this prepare the environment or set the parameters. Here we're going to specify some of the functionality in the notebook. For example, is termination selection interactive or not? We just need it false. Then we're going to provide Miller indices, thickness, vacuum, supercell matrix, orthogonal C, use conventional cell, and slab termination formula if we know any, and the termination index in case it's a fallback in case there's multiple terminations, you didn't provide any, it selects the 0th one. Usually, when you selected material, selected the correct properties, you can hit just run all cells, and we see that the kernel is busy. We install the packages for each notebook. Okay, packages installed. Then we should retrieve a material from the selection. Materials are loaded each time you reload the notebook or you restart the kernel. So if in case material doesn't show up, you can just restart the kernel or reselect the material, reselect the notebook. Okay, here we have the silicon material pre-visualized. We can review what was happening here. It selects it analyzes material for the terminations, and returns material for each termination. There's just one termination for silicon. We build here the main function that creates a slab with all the parameters that provided, and as a result, we can preview it, and it's passed to the selected materials out portion. You can select any materials that you want to pass and submit, and we have the final structure. You can toggle on bonds and preview it. Let's get back to next example. Next example is going to be germanium 001 on silicon 001 interface. with no strain matching. So we need to provide our own transformation matrices. We will take silicon and germanium bulk and create the material. We'll define silicon slab, germanium slab, then we'll define the interface between them, and then we're going to build one. For germanium, germanium slab is the same as for the silicon, similar approach, but we first need to get the material. So for that, we import material from StandData. We go to input output. Inside the material designer, we go to input output, import from StandData. The pop-up should come visible, and then we search for germanium and we submit. We select it and we submit. Then we have the material, two materials in the working list. Then we're going to define both slabs. We have the same parameters for this for both of them, the same as we've seen just now. And we need to provide film indices for the notebook to know which index, which material to use as which type of material. And here at the bottom, we have settings for the interface. In this case, interface distance is going to be 1.2 angstroms, and the interface vacuum is going to be 0 because it's going to be a bulk interface. Next, we're going to create slabs with the same function that we used before, providing all the parameters that were specified. And then we get to the creation of the interface with the help of the function. We pass film slab, substrate slab, and gap and vacuum. Also, we can provide XY shift to shift the film in angstroms relative to the substrate in XY direction. And as a result, we should get an interface seen from different directions. Okay, let's look over this. Probably we go to input output, import from StandData. So StandData has a set of materials. For example, we can see germanium is at the bottom, and we can search by for example, by the name. We can find germanium. We can search by formula. We can search by, for example, by the lattice type and get all the FCCs. You can search for monolayer, for example, and find all of the materials that have monolayer in them. But we want to search for germanium right now, and yes, we'll select it and submit. Then we're going to go again, advanced JupyterLite transformation. Reselect germanium that we want, and again, go to the slabs. And since nothing has changed, we might just run all cells. Packages are needed to be installed again, because each time we close and open the JupyterLite session, all the progress is reset. So you need to install all the packages again. So all the same as for silicon, and as a result, we should get the final material. Yes. Now we want to build the interface. Also, sometimes you don't want to lose progress in the notebook. So for that, we have a different way to open the notebooks and not to work with the materials here. If we go to View JupyterLite Session, so it's View JupyterLite Session, we can open a drawer and we can slide it. And for example, we can hide it so that we can work with the materials, review them. So to create interface, we go to multi-material structures, interface without strain matching. So the slab of silicon and germanium, they have close match. For the lattices, So we can just use 0, 0. We can just use unary matrix for the supercells. We open the notebook, and here we need to specify the parameters for the interface. So film thickness for the film, we need to provide germanium FCC. So this is going to be index 0, 1, 2. So second one for the substrate is going to be silicon. So yeah, it's 0, correct. But also we need to change to make it 0, 0, 1 and just one thickness. Vacuum not needed, can be 0. Interface distance, we wanted to set 1.2, and here are vacuum we don't need. So if we hit run all cells, we should get all the installation, and then we should get the final material. For materials retrieved, you should search for the terminations. We have just one termination for each. Okay, that's correct. We create slabs as was shown before, and then we create the interface. Okay, there's some. I think maybe something was specified incorrectly. Oh, okay. I see the issue. I think I provided the wrong. I'm using primitive cells instead of conventional cells, so it might not work correctly. We can just go here and yes, use conventional cell. That's what we need to do. We just rerun, and the package is already installed, so it should just go. Okay. Also, I can see that the kernel says it's busy, but nothing is running. I think it's a perfect opportunity to show what to do in case you encounter any issues. Sometimes notebook PyDat can be slow or can have some issues. So if it's just stuck, you can reselect the kernel. It should change it to idle, or you can reload restart the kernel. Then kernel is idle, and we need to rerun cells. Again, installation happens because we reloaded the cells, but usually it's quite fast. Okay, all the materials selected. Okay, I think it fall back on the wrong input. I think it didn't get the materials.
Explain which materials it gets and from where.
Yes. So right now you can see it didn't get the materials from the list for some reason, but we have the fallback materials. So I had some from previous work. I had some materials, so it loads materials from the uploads folder in case there's no materials provided in the list. But it should not be happening. Okay, let's just. It should get the materials, so I should see them here. Okay, probably just let's run all cells again. Okay, this is correct, and we should get the correct interface as a result. All right, it's pre-visualized, and yes, as a result, we get the correct interface. So I think it provided thickness of 1. Okay. So let's get to another example. So this was, sometimes you need to select more terminations. And for example, strontium titanate 110 can provide such example. We can have terminations of O2 or strontium titanate O. So we want to get the bulk material and create two different terminations. We import some data and import material from some data as it was done previously, instantiate the material. Then we use the create slab function to specify correct Miller indices. And for termination formula, we use O2 or strontium SrTiO, and just number of layers 1, vacuum, and all the rest are the same parameters as before. And as a result, we should get two materials with different terminations. For this, we can open the material designer again. I'll probably close this one to not to interfere. This I'm going to show you with the another functionality that we have. So let's go to the view JupyterLite session again. Here we have specific examples. It's a folder that has all of the notebooks where we reproduce some of the publications. So if we go to the Slab strontium titanate right now, we can see that we are reproducing material from this paper. Here, everything's provided. So Miller indices are selected, thickness is set. So we can just run all cells. Again, Python, PyDiet kernel was idle, now it's busy. We install all of the packages. Input materials here will come from StandData. So StandData create get by name first match. So we can preview material with the repetitions. And then it searches for the terminations with the helper function. So in case you don't know the terminations, you can search, you can find them with the get slab terminations helper function, finds in two different terminations. And then we create a set of slabs for each termination. And we have two slabs. As you can see, they're downloaded. So this function sets materials into the working directory. So we can preview them here. Strontium titanate and oxygen terminated, as well as JSON files were downloaded on the machine. So you can preview materials here. Use materials here. Excuse me. So now let's get to the interfaces example. We're going to use ZSL matching to construct graphene on nickel interfaces. So the same approach, we want to create this material. We start with graphene and nickel bulk. We define the slabs for them. We use ZSL analyzer to find strain matching configurations for the interface. And then we're going to build interface. So define, refine, and build. Again, we import materials. As you can see, we can search by the colloquial name here. We instantiate material classes. Then we define substrate slab with the same create slab function as before. And Miller indices termination formula, although it's not needed because nickel has only one termination number of layers. And then we can see that arguments below are omitted. They can be omitted because they're default. So each function that we have has some sensible defaults for each of the argument. So you don't need to provide all of them. Usually they'll have something simple, like no interference. So it's just singular matrix, or it's all orthogonal, etc. We then define the Graphene slab with the similar approach. And again, these all default parameters. And next, we're going to import DSL interface analyzer, pass it the film and substrate slab, as well as maximum search area and any other parameters for the search. Then we can get the interface configurations with the get configurations. And for example, we can get if lowest strain is the 0th one. So we rank them by lowest strain and then by lowest size. So 0th is usually the lowest strain as well as lowest possible size for the strain. We can plot the strain versus number of atoms, the size of the cell, to search for the index that is most optimal for your use case. And then when we find the configuration, we can create interface and provide the index if we need to. Or it will give you the most optimal, the lowest strain. We import create interface function, provide the film and substrate configurations, XY shift in case there's any shift for the film, gap and vacuum. And as a result, we should get the material. So let's get to the hands-on demonstration. Again, I follow materials designer Mat3ra.com for each. Also important to note that usually it's best to have just one interface to one pyadiode, because they might interfere with each other if there's more than one open in the same browser. Okay, so we want to create nickel graphene interface. We're going to import from stan data. Let's start with the nickel and graphene monolayer. Okay, it's correct. We'll remove the silicon to make some room. Then we're going to open JupyterLite session, scroll to the multi-material structures interfaces, and we want interface with ZSL strain matching. Again, it explains how to use it. Film is index 1. We want to set substrate 0 index 0. Film looks all correct. Substrate, we want to change millimeters to be 111. Thickness 3, everything's correct. Let's change it to distance from the literature. Interface looks right. Use conventional cell again. Then we provide parameters for the search algorithm. For materials that have similar lattice types, it's usually small maximum area of around 100, 150, 200 is useful. If materials have different types, you might want to get a larger area, 250, 500. But again, the larger the area, the longer is the search. Okay, let's hit run all cells. Get to materials. We should preview them shortly. Then it searches for all the terminations for each slab, and we'll find just one termination for each. We'll preview said atomic layers. This is actually the blocks through which the thickness is measured. So 3 thickness for this slab is going to be 3 layers of this layer. We define the slab configurations, and then the ZSL analyzer searches through them on the max area, and as a result, we get matches, and we can plot them. So most optimal, usually on the left lower corner. Again, strain half a percent, it's good. There's some more strange structures. So again, depending on the task, you might need different trade-offs. So selected index is 0. You can select any other index if you need to. We'll get to that in the next example. And then we create interface between slabs using the helper function. And as a result, we get the simple, familiar interface. I toggle bonds with the hotkey of B, by the way. Okay, let's look what we can do if we change interface to be nickel 001, for example. We can change 001. Size, I think, is going to be the same max area. Everything, the rest is the same. We can just run all cells again. And again, it was fast this time because we don't need to install anything. Let me check. Maybe we didn't get the most optimal interface. Oh yeah, so 0 strain, it's this interface. It has some strain, but we do get this material. Okay. It has 8% strain. And yeah, you can see that the graphene is a bit strained in one direction. So that's where the 8% comes from. We can, for example, toggle off the bonds and view, like increase the atom radius to make it easier to see that is indeed 001 orientation. So we can see these squares here. So 001 on graphene. Okay. As we mentioned before, this can be used not only on the web, but also in your own IDE. So all the notebooks are available on GitHub and PyPy. And yes, for example, we use Pycharm in our work. It's just a Python IDE, the same as VS Code or any other. Here we can see that I have API examples package cloned. If we go to other materials designer, they should be all the notebooks that we've seen in the web version, as well as uploads folder, specific examples with all the papers. So we can open the create interface with Vinium ZSL, and we have some uploaded materials here. So JSON for nickel and graphene, as well as some CF and nickel postcards. There's notebooks that handle imports of different types of materials. And we can just run it here. Again, 001 on 1. It's all the same parameters. We can just hit. Installation here happens at the level of the environment. So it's different whether it's Conda, Venv, or whatever you might use. And it should be fast. It loaded the interfaces. It loaded the materials from the uploads folder, review them, ran the same logic as it was in the web version. We get optimal strain and some other materials to choose from. And again, the same material, we can preview it here. And it should be uploaded to uploads. Yes. Let me show that we can. Drop materials here to check to compare it. Input output upload from disk, and we can drop this material JSON or postcard file into the preview. Okay, this is the material. This is what we got. This is what we got in the web version. This is what we got with the IDE. They the same because we provided the same parameters. So we have notebooks for all typical use cases, and they're also available at the JupyterLite Mat3ra.com. So here, if you go to made, this is the made package. Referring to the made package, we have all the notebooks. Again, if we scroll somewhere down, should be introduction notebook where you can use links. So this is what we've seen in the materials designer. version, but it's just on the internet as a standalone option. And you can browse and run different notebooks here for the to learn how to use different aspects of the platform of the package. Again, Materials Designer is on materialsdesigner.mat3ra.com as well. It's maybe I should show that it's available on the platform as well. So yeah, in case you just work with the platform, this Materials Designer is available on the platform. So if you want to create material, the same interface, advanced JupyterLite transformation, and it should present you with the, again, selected materials, and everything is the same, and as well as the JupyterLite session drawer. And you can use it on the platform. Okay, so as a summary, today we presented Mat3ra Mate package, which is a Python framework for the design of 2D materials. We introduced API examples, which is a set of Jupyter notebooks that provide examples for real-world 2D materials applications. They're available on JupyterLite.mat3ra.com, as well as inside of the Materials Designer and web application, and available on GitHub. And we showcase the Materials Designer app for materials handling and use of the JupyterLite transformation. All code is open source and available on GitHub and PyPy, and we welcome contributions and any suggestions. And I think now it's time for the questions.
All right. Thank you, Seth. I'll open the floor for questions. If you would like to speak up and ask questions through the microphone, please raise your hand. Otherwise, we're going to look through the Q&A and the chat. I don't think I see any questions as of yet. So maybe let me start with the questions myself. Most of the time, people would probably work with some existing formats like Pycharm or CIF when handling their materials data. Maybe we can talk a little bit about how, if you already work with some particular format, how you can use it in our code base.
Yes, so we can import some of the materials from the Pycharm or CIF files. If we open the JupyterLite session again, we might see we have specific notebooks to show how to import materials. So I think at the bottom we have other, import from files in AC supported formats. So we rely here on the AC to import all of the materials that all of the versions that it supports. And again, it reads from uploads folder. We have some files here. We have some CIF Pycharm file. So let's see if we run all cells, it should load all of the materials that are in AEC format here. So we expect to see CIF and nickel. Okay, kernel is unknown. Did they close it? Yes. JupyterLite is open, that's why. Okay, idle. Okay, so it didn't read the JSON files, but it did read the CIF and Pycharm file because this is AC supported options. Graphene and nickel was read. Then this is just the helper troubleshoot table that shows all of the possible formats because it doesn't know that the JSON file exists. Yes, and then we convert AEC atoms to our structure, and we can see that we loaded materials, nickel and graphene, and they were sent to the working directory.
All right, we do have a couple of questions coming in the chat. We have a question from Silva. How to use the software for biological applications like nanoparticle generation? We intentionally stay away from biological applications because we believe that there's quite a bit of different capability in the field already. But as of the nanoparticle generation, we have some ways to help there. I think you can, you can talk a little bit about the nanoparticle generation capability that we have.
Yeah, there is example in the paper that we reproduce. Okay, first of all, we have the notebook to create spheres, clusters or a nanoparticle. I may show you the notebook where we reproduce the paper. So nanocluster gold, and here we reproduce the paper where some of the gold particles are created. So we expect to create nanoparticles of various forms from gold. And it shows how to use the notebook.
Yeah, this, by the way, will be a topic for one of the future seminars. So as today we're focusing on the basics, in one of the next webinars we'll focus on some of the specific examples on how to reproduce them using this toolchain. But as for nanoclusters and things like nanowires, nanotubes, the capability to design and create them is included in this code base. I hope that answers the question for Silva. We have the next question from Malindo, and it is about can it be done for interface of sodium-3, vanadium-2, okay, PO4, bulk, and okay, quite complex compound. And I believe if we get the structures for these materials, then we should be able to create an interface for them. But as long as you have postcard structures for both of these compounds, we should be able to put them together and create an interface. Maybe if you have specific details about those structures, or if you want to get some help, we can have a more detailed chat. Several will provide the contact details and we can discuss it offline, Amalindo. And then the second question from Amalindo was about how to load the CAF to STEM data. Maybe we can explain once again.
To STEM data or to the materials designer, because STEM data is a database that is primarily created from. Well,
so for STEM data, let's explain how people can contribute, right? What it is and how people can contribute, and then we'll explain how to use CAF inside the Materials Designer.
Yeah, so STEM data is a standalone database for most commonly used materials, and you add materials with the via GitHub. So STEM data has, if we go to the materials, it should have the materials sources folder where you provide, you can load the postcard, and then we have the then you need to provide, or there should be a manifest file, manifest YAML, that shows where you provide the name and all the properties for the material. So the space group, dimensionality, form factor, as well as the links to the origin of the material. And then if you run locally on your environment, if you run build materials, then materials will be created, and you need to create the pull request, and then we can merge it into the main database. So the plan is to have all of the most commonly used materials here. So it's done in a software way. It has the README in case you want to contribute. It explains how to use it. Is it enough for the
for CIF? Let's
standard?
just look at it once again.
Well, we can load. Okay, so for to load material, we need to go to the open the Jupyter session, go to uploads, and for example, we can just drop a material here.
So we'll drag and drop the CIF file into the uploads folder and then run the import materials notebook, right?
Yes, and run import materials notebook. So it was the same as was before. So if I just don't have any CIF files on me right now. So
that's okay. We have one over here, and it demonstrates the approach. Hope that answers the question from Amolendo. And then we have another question from Ashby. The question is about what might be the best package I can choose to study surface electronic properties and surface defects. Well, we are obviously biased, but I think you can start with Mat3ra made as we've been discussing today. So we intentionally just focus on the creation of material structures today. But as part of our code base, as part of our infrastructure, we have the capability to simulate the structures and extract their electronic properties. For example, one thing that we'll go over in the rest of this webinar series is how to calculate valence band offsets for an interface to understand how electronic transport can be done through this interface. And we'll cover this use case in details as we go forward. There are plenty of other libraries that maybe that's what we could discuss. What are the dependencies of Mat3ra made and how people can contribute to this package as well. So we have open source code base that you can access on GitHub. So if you go to our GitHub page, we are at github.com/exabyte-io. And you can see all the packages that we've been discussing at that page. This is the introductory page for the company and our efforts. And now the package that we discussed today, Mat3ra made, it depends on other community packages like PyMagen and ASE, but most of the capabilities are drop-in. So for example, PyMagen could be sometimes complicated to install, and as you can see, you can install Mat3ra made in different flavors. So if you just want the basics, you install it without any particular flavor. If you want additional tools that we've been discussing today, you install Mat3ra made with tools. And if you want to contribute you would install it with tests and development environment. Okay. Looks like we answered that from Amolendo, and then we have two questions from Yulia. Can this programming be used for modeling properties of bulk materials? It's only useful for modeling 2D materials. Seth, I'll give that to you.
Well, as we've seen right now, we used some of the bulk materials as well. For example, we have examples to just create defects or bulk interfaces or any other types of materials. So yes, you can create bulk materials. For example, we can get well. The short answer is yes. We just need to know what we need to do. For example, we could just add a point defect. There's a notebook for that, where you import the material and then you add the defects.
Yeah, to sum it up, I think you can go back to the slide with categorization. So that's what we started with on the beginning. And it demonstrates the approach. So in our view, any kind of materials you should be able to create with the help of this framework. But today, and as part of the series, we're focusing specifically on two-dimensional materials because a lot of interesting effects happen at the interfacial layer. And we want people to be able to study those. But we can also facilitate the creation of defects like grain boundaries or commensurate lattices or point defects, vacancies, and things like that inside bulk materials. And the second question from Yulia was about can the influence of temperature and pressure on material structure and properties of the materials be modeled with your program? The answer is yes, and that's something that we will cover as part of the future webinar series. Today, we're focusing only on materials design, so the portion where we design the structures. And then the second step would be to apply specific modeling techniques like density functional theory, or we can look at molecular dynamics or foundation models to be able to simulate the structures and then apply temperature, pressure, and things like that. All right. As we are running a bit over time, I think it's time to wrap up for today. Let me just look at the Q&A session once again. All right. With that, we'll thank our presenter, Seb. We'll thank everybody who joined us today, and we will meet again next month, last Wednesday of the month, where we will continue this webinar series and look at more complicated use cases, including how to build heterostructures and commensurate lattices and grain boundaries, defects, and so on. All right. Thanks, everybody. Bye.